There is a galaxy in the sky that you can see with your own eyes. No telescope, no spacecraft, no machine between you and it. Just darkness, patience, and a faint blur of light that has been crossing space for 2.5 million years. That blur is Andromeda. It does not look like a place. It does not look like a destination. Under a truly dark sky, it looks like a pale smudge, a soft stain in the blackness. Something you might mistake for a thin cloud if no one told you to look carefully. Yet inside that blur are hundreds of billions of stars, worlds no human has ever seen. Dead suns, newborn suns, black holes, nebulae, star clusters, and the long, slow architecture of another galaxy. Andromeda is one of the nearest great galaxies to the Milky Way. It is close enough that its light can enter your eye without help. It is close enough that ancient people saw it long before anyone understood what a galaxy was. It is close enough that we can point cameras at it and resolve parts of its disk into individual stars. But it is also so far away that the word nearby becomes almost meaningless. The light from Andromeda began its journey before writing, before cities, before agriculture, before nearly every human story that feels old to us. It began crossing space before our species had built its first temples, before anyone had named the constellations, before anyone had looked up and wondered whether the lights in the sky were gods, fires, spirits, or worlds. The galaxy is visible. That is the trap. The sky makes distance look flat. It turns the universe into a ceiling. It places the moon, the planets, the stars, nebulae, and galaxies on the same dark surface as if everything above us were merely painted at different levels of brightness. The eye sees a dome. The mind has to learn depth. Tonight on Dark Matter Radio, we are going to stay with one question that sounds simple until it begins to break apart. Could humanity ever reach Andromeda? Not see it, not photograph it, not measure it through telescopes. Reach it. Send something across the gap between galaxies and have it arrive. The question begins with rockets. It does not end there, because Andromeda is not merely far. It is far in a way that turns travel into philosophy. It forces us to ask what a journey means when the trip lasts longer than civilizations. It forces us to ask whether speed is enough, whether survival is enough, whether arrival still matters if the beings who arrive are no longer like the beings who left. And if every ordinary road fails, it leads to a stranger thought. What if the way to reach Andromeda is not to cross the distance at all? What if the only road to another galaxy is not through space, but through spacetime? Begin with the smudge. The Andromeda galaxy is catalogued as Messier 31. Astronomers often call it M31. It lies in the direction of the constellation Andromeda, where dark skies reveal a faint elongated glow. It is not the closest galaxy to us. Smaller dwarf galaxies orbit the Milky Way much nearer, but Andromeda is the nearest major galaxy, the great spiral neighbor that most resembles the kind of cosmic island we live inside. That matters because we cannot step outside the Milky Way to look back at it. We live embedded in its disk. We see its structure from within, the way a fish might study the ocean while never leaving the water. Andromeda gives us a kind of mirror. It is another vast spiral system close enough in cosmic terms for us to study in detail, but close in cosmic terms is not close in human terms. Andromeda is roughly 2.5 million light-years away. A light-year is not a time. It is a distance. It is how far light travels in 1 year through vacuum, moving at about 300,000 kilometers every second. That number is already too fast to imagine. Light can circle Earth more than 7 times in 1 second. It can travel from the moon to Earth in a little over a second. It can reach us from the sun in about 8 minutes. Yet even light needs more than 2 million years to cross the distance from Andromeda to us. The human mind is not built for that scale. We can say 2.5 million light-years, but the phrase arrives too neatly. It is too clean. It fits inside a sentence, so it feels smaller than it is. Try another way. If the sun were a grain of sand, the nearest star system would still be kilometers away on the scale of ordinary experience. The Milky Way would become a geography too large to walk, and Andromeda would not be a neighboring house. It would be another continent in a world where the continents are separated by black oceans without ships. Even that analogy fails. The real universe is emptier. The strange thing is that Andromeda also has size. It is not a dot waiting at the end of the journey. It is a galaxy roughly 150,000 light-years across. depending on where one decides its faint outer boundaries end. It is wider than the Milky Way in some measures, though mass estimates and halo structures complicate every simple comparison. It contains an enormous stellar population, perhaps on the order of 1 trillion stars by some estimates, mixed with gas, dust, globular clusters, dark matter, and a central supermassive black hole. So the target is not small, it is only the gap that is terrifying. From Earth, the Andromeda galaxy spans several degrees of sky if you include its faint outer regions. In photographs it can look much larger than the full moon. But our eyes are poor collectors of light compared with long-exposure cameras. We see mostly the bright central region, the old bulge where many stars are packed together. The spiral arms are there, but they are too dim for casual sight. This is another lie the sky tells. Things can be enormous and nearly invisible. Things can be close in astronomy and unreachable in engineering. Things can be ancient by the time we see them, yet present in the same night as our breath. A person under a dark sky might look at Andromeda and feel that it is waiting. Physics gives a colder answer. It is not waiting. It is simply there. And the universe has placed a distance between us that mocks almost every machine we have ever built. To understand why, do not begin with the most advanced spacecraft in science fiction. Begin with the spacecraft we actually sent. Voyager 1 left Earth in 1977. It used gravity assists from the outer planets and eventually became the first human-made object to enter interstellar space. It is one of the fastest escaping artifacts humanity has ever launched. It is also, by galactic standards, almost still standing still. A Voyager-like spacecraft would take tens of thousands of years just to approach the distance of the nearest stars. Andromeda is not the nearest star. It is hundreds of thousands of times farther away than Alpha Centauri. If you imagine sending Voyager toward Andromeda, the result is not a mission. It is a gesture, a message in a bottle thrown into an ocean so wide that the bottle may outlast the species that made it and still not reach another shore. Current chemical rockets are built on a brutal limitation. They throw mass backward to move forward. The faster you want to go, the more energy you need, and the more propellant you carry, the more energy you need to move the propellant itself. This is the tyranny of the rocket equation. It is not a lack of ambition. It is mathematics pressing its hand against the door. Chemical rockets are magnificent for leaving Earth. They are not serious tools for crossing between galaxies. So we imagine better engines. Nuclear thermal rockets where a reactor heats propellant and throws it out faster than chemical combustion can. Fusion rockets where the same process that powers stars is controlled inside a ship and turned into thrust. Antimatter rockets where matter and antimatter annihilate and release energy with extraordinary efficiency. Laser sails where enormous beams push thin reflective craft across space without the craft carrying all its own fuel. Each step improves the dream. Each step also reveals how far the dream has to go. Suppose a future probe could travel at 10% of the speed of light. That would be astonishing. It would cross the distance to the nearest stars in decades, not tens of thousands of years. It would make interstellar exploration imaginable. At 10% of light speed, Andromeda still takes about 25 million years from Earth's frame. 25 million years is not a long mission. It is a geological interval. It is a timescale over which continents shift, climates transform, species emerge and disappear, and the surface of Earth forgets the names of everything we built. Increase the speed. At half the speed of light, Andromeda still takes about 5 million years from Earth's frame. At 90% of light speed, it still takes close to 3 million years by the clocks left behind. At 99.9% of light speed, Earth still waits roughly 2.5 million years, because from Earth's perspective, nothing moving through space can outrun the light that defines the distance. The ship may experience time differently, but the galaxy does not become close for those who remain. This is where relativity enters with a gift that feels almost cruel. Einstein tells us that time is not absolute. A clock moving very fast relative to you ticks more slowly from your point of view. This is not a trick of perception. It is built into the structure of spacetime. Particles accelerated near light speed live longer than they would at rest. Atomic clocks flown on aircraft or placed on satellites do not agree perfectly with clocks on the ground. The global positioning system has to account for relativity, or its accuracy would drift. At everyday speeds, the effect is tiny. At extreme speeds, it becomes enormous. A traveler moving close enough to light speed could in principle cross a vast distance while experiencing far less time than observers on Earth. The journey to Andromeda might last millions of years for Earth, but far less for the traveler if the speed were close enough to the cosmic limit. That sounds like a loophole. It is one, but it is not a free one. To make time dilation dramatic, the ship must reach speeds extremely close to light speed. The energy required grows without mercy. As a ship approaches light speed, adding more speed requires more and more energy. You can get closer. You cannot reach light speed if you have mass. Even if the energy problem were solved, the environment becomes dangerous. Space is empty, but not perfectly empty. It contains gas atoms, dust grains, cosmic rays, and magnetic fields. At near light speed, a grain of dust is no longer a speck. It is a bullet carrying devastating energy relative to the ship. Interstellar hydrogen becomes a radiation storm. The direction of travel becomes a weapon pointed at the spacecraft. Shielding is not optional. Navigation is not simple. Acceleration is not gentle. If humans are aboard, they cannot be slammed instantly to relativistic speed. They must accelerate over time. If the acceleration is comfortable, the trip profile changes. Then they must decelerate at the other end, which requires enormous energy again. A flyby of Andromeda after millions of years would be a strange kind of failure. Arrival means slowing down, and slowing down is just another form of acceleration with the same impossible bill. Relativity can shorten the experienced journey for the crew. It cannot shorten the distance for the universe. That is the cruel gift. The traveler might survive a trip that the home world experiences as deep time. A crew might step out near Andromeda having aged years, decades, or centuries, depending on the speed and acceleration profile. But Earth would have moved through ages. The language that launched them might be gone. The species that launched them might be gone. The sun would be older. The Milky Way itself would have changed. A mission to Andromeda is not only a question of speed, it is a question of whether arrival has meaning when departure belongs to a vanished world. There is another way people imagine surviving the distance. Instead of sending a crew that remains awake, send a world. A generation ship is a spacecraft large enough to support a human community for many generations. People are born aboard. They live aboard. They die aboard. Their descendants inherit the mission. The ship is not transportation in the ordinary sense. It is a moving homeland. For a nearby star, this idea is already difficult. For Andromeda, it becomes almost mythological. A generation ship lasting millions of years would need to preserve air, water, food, knowledge, social order, biological health, technical skill, and purpose over a time span longer than any civilization has survived by orders of magnitude. It would need ecosystems that do not collapse, machines that can repair themselves, cultures that do not abandon the mission, and archives that can remain intelligible across changes in language and mind. The first crew would not reach Andromeda. Their children would not reach it, nor their grandchildren. Millions of generations might pass, depending on the speed. At that point, the word mission changes. It becomes ancestry. It becomes religion. It becomes environment. The destination may become a myth inside the ship, a bright story told by descendants who have never known a planet and cannot truly imagine one. Would they still want to arrive? Would arrival be a liberation or a catastrophe? A society born in an artificial world may not be suited to a galaxy. It may not recognize Earth as anything more than an origin legend. Its biology may change. Its culture certainly would. It may become adapted to the ship, not to planets. It may decide that the moving habitat is home, and that Andromeda is an old obsession inherited from people who died before memory. The generation ship reveals something uncomfortable about intergalactic travel. At some scale, exploration stops being an act performed by humans and becomes a process that manufactures new kinds of humans. There are alternatives. Cryogenic sleep, if biology ever permits it safely for long durations. Embryo ships, where frozen embryos travel with machines that raise humans after arrival. Artificial intelligence probes, carrying no human bodies at all. Mind uploading if minds can ever be copied or sustained in artificial substrates, a claim far beyond current science but common in long-range speculation. Each alternative dodges one problem by creating another. Cryosleep must keep bodies intact across time, radiation, and failure. Embryo ships require machines to become parents, teachers, doctors, and cultures. AI probes avoid human fragility, but then the question becomes whether the mission is still human exploration or simply human-made exploration. Uploaded minds raise even deeper questions about identity. If a copy of you arrives, did you arrive or did something patterned after you wake up under another sky? Andromeda does not merely demand better engines. It demands a theory of continuity. What exactly has to survive for a journey to count? The body, the mind, the species, the message, the intention? A stone thrown from Earth could reach another galaxy in some remote future if it were aimed perfectly and survived. No one would call that exploration. A robot could arrive and send data if anything remained to receive it. A civilization could launch a self-replicating probe that spreads through Andromeda millions of years later. Would that be a triumph or only a delayed echo? This is why the question becomes darker than it first appears. Can we reach Andromeda? The word "we" carries more weight than the word "reach." There is one fact that gives the story a strange twist. Andromeda is not sitting still. The Milky Way and Andromeda are part of the local group, a collection of galaxies bound by gravity. For a long time, the standard story was that Andromeda and the Milky Way were destined for a future collision or merger in several billion years. The galaxies are moving toward each other. Their mutual gravity matters. In many models, they eventually pass through one another, stir their stars into new orbits, and settle over time into a larger remnant sometimes nicknamed Milkomeda. A galactic collision does not mean stars smashing into stars like sparks in a fire. Galaxies are mostly empty space. When two galaxies merge, their stars mostly pass by one another at great distances. But gas clouds collide, star formation can ignite, black holes can sink toward the center, and the structure of both galaxies changes. That older picture had a peculiar comfort. Maybe we never reach Andromeda because Andromeda eventually reaches us. But even that future is not as settled as it once seemed. Recent work using updated data from Gaia and Hubble has made the long-term Milky Way-Andromeda encounter less certain than older simplified descriptions suggested. The gravitational influence of other local group members, especially the Triangulum Galaxy and the Large Magellanic Cloud, complicates the outcome. Some simulations still produce a merger. Others allow a near-miss or delayed interaction. Over 10 billion years, the future is not a single line. It is a spread of possibilities. This is a useful correction. Cosmic destiny is often told too cleanly. Galaxies are not beads sliding on rails. They are vast gravitational systems inside a moving group of other systems, all measured with uncertainties, all sensitive to mass estimates and velocities that are difficult to know perfectly. Even when gravity is deterministic in principle, prediction becomes fragile when the data are imperfect and the timescale is immense. So Andromeda is both approaching and uncertain. It may merge with us. It may not merge within the next 10 billion years. It may pass close enough to reshape the local group in ways we cannot yet state with final confidence. The unsettling point is not that one outcome is guaranteed. The unsettling point is that even the future of our own galaxy is a calculation still being revised. If humanity ever tries to reach Andromeda, it may be aiming at a target whose relationship to us changes across the ages of the mission. The galaxy is moving. The Milky Way is moving. The Sun is orbiting the Milky Way. Stars drift. The local group evolves. A journey lasting millions of years must navigate not to where Andromeda appears, and not even to where it is now, but to where it will be when the mission arrives. That sounds ordinary. Ships have always aimed ahead of moving targets, but here the target is a galaxy. The arrow is millions of years long, and the map itself evolves while the arrow flies. At this point, ordinary travel begins to feel like the wrong category. A rocket, however advanced, still accepts the distance. It crosses space 1 meter after another. It may cross faster. It may carry better shields. It may exploit relativity. But it still plays by the rule that Andromeda is far away and the path must be traversed. A wormhole changes the question. Not by making the traveler faster, by making the path shorter. In popular imagination, a wormhole is a tunnel through space. That is not completely wrong, but it is too simple. In general relativity, gravity is not a force in the old Newtonian sense. It is the curvature of spacetime. Matter and energy tell spacetime how to curve. and curved spacetime tells matter how to move. If spacetime can curve, then one can ask whether it can have non-trivial topology. That phrase sounds cold, but the idea is powerful. Could the geometry of the universe contain shortcuts connecting distant regions? Could two places that are far apart through ordinary space be near through a deeper geometry? The classic picture is a sheet of paper with two dots drawn far apart. If you travel along the paper, the distance between the dots is long. Fold the paper so the dots touch, and a shorter path appears through the fold. The analogy is useful, then dangerous. Space is not literally a two-dimensional sheet floating in a higher room. We do not know of a cosmic hand that folds it. The fold does not happen in the way paper folds. The real mathematics concerns space-time geometry itself, and the details are far stranger than the drawing. Still, the image points toward the essential idea. A wormhole would not let you locally outrun light. It could allow a route where the distance through the wormhole is shorter than the distance through ordinary space. You obey the speed limit in your local tunnel. But the tunnel connects places that are otherwise separated by enormous distance. This is why wormholes are so tempting. They do not simply offer speed. They attack distance. The most famous serious study of traversable wormholes came from Michael Morris, Kip Thorne, and Ulvi Yurtsever in 1988. They examined the possibility of wormholes that could, in principle, be passed through by humans without immediately destroying them. The result was not a blueprint. It was a theoretical exploration showing that if such wormholes are allowed, they require matter and energy arranged in ways that violate familiar energy conditions. In plainer language, a stable traversable wormhole appears to need something like negative energy or exotic matter to hold its throat open. That phrase, exotic matter, is easy to misuse. It does not mean rare minerals or strange crystals. It means stress energy with properties unlike ordinary matter. Ordinary matter has positive energy density. It gravitates in familiar ways. A traversable wormhole throat tends to want to pinch shut. To keep it open, the geometry must be supported by something that acts against that collapse. Quantum field theory does allow small negative energy effects in special contexts. The Casimir effect is often mentioned, where conducting plates placed extremely close together can alter vacuum fluctuations and produce a measurable force. But this is not the same as having vats of negative energy waiting to be poured around a wormhole. The scale, control, stability, and engineering are beyond anything known, so the honest position is narrow but fascinating. Wormholes are not known to exist. No telescope has found one. No spacecraft has passed through one. No laboratory has built one. But they are not simply fantasy pasted on top of science. They arise in the mathematics of general relativity under certain conditions. Some versions are non-traversable. Some are unstable. Some require ingredients that may not exist in usable form. Some modern theoretical work explores quantum connections, black holes, and spacetime in ways that keep the word wormhole alive. Though often far from the science fiction image of a ship-sized tunnel, that is the strange category. Mathematically serious, physically unconfirmed, technologically unreachable, a wormhole to Andromeda would be more than a vehicle. It would be infrastructure made from spacetime itself. Think about what would be required. First, a wormhole would have to exist or be created. If natural wormholes exist, we would have to find one. It would have to be traversable. It would have to have one mouth accessible to us. It would have to connect to a useful destination. The chance of a naturally occurring stable wormhole with one mouth near the solar system and another near Andromeda is not something physics gives us reason to expect. If we create one, the problem becomes even larger. We would need a theory of quantum gravity or some deeper control of spacetime that we do not possess. We would need to generate and shape gravitational fields at extreme scales. We would need to hold a throat open against collapse. We would need to prevent catastrophic tidal forces. We would need to keep radiation under control. We would need to know whether passing matter through changes the wormhole in dangerous ways. Then comes the destination problem. Even if you could make a wormhole with two mouths in the same laboratory, one mouth would have to be moved to Andromeda or connected there somehow. Moving a mouth to Andromeda by ordinary means brings back the original travel problem. If the mouth must be carried across space at sublight speed, The shortcut is only useful after someone has already done the impossible trip. This is a detail fiction often hides. A wormhole network may need to be seeded. The first route still has to be established. Unless wormholes can be created with distant mouths already linked, or unless natural mouths already connect far places, the first connection to Andromeda demands a feat before the shortcut can become useful. And if a wormhole can connect distant places without physically moving a mouth there, then we are not discussing engineering as we know it. We are discussing control over the global structure of space-time. That is not a better rocket. That is a new relationship with the universe. There is another complication. Wormholes and time machines are uncomfortably close in the mathematics. Morris, Thorne, and Yurtsever explored how a traversable wormhole could be converted into a time machine under certain conditions, for example by moving one mouth relativistically relative to the other. Time dilation would make the mouths age differently. A traveler passing through could emerge at a time that creates causal paradoxes. This does not prove wormholes cannot exist. It shows that if they do, they sit near the deepest rules of causality. Stephen Hawking famously suggested a chronology protection conjecture, the idea that the laws of physics may prevent macroscopic time machines from forming. But conjecture is not proof. The universe has not handed us the final answer. A wormhole to Andromeda might not only be a shortcut across space, it might be a challenge to time. The same structure that makes distant places near could make different times entangled in dangerous ways. The engineering question becomes inseparable from the question of whether the universe permits causality to be bent without breaking. This is why wormholes are beautiful and frightening. They are not doors placed inside space. They are possible distortions of the stage on which space and time occur. To imagine one as a simple tunnel is to make it too small. If a future civilization built a stable wormhole to Andromeda, it would not mean humanity had invented a fast ship. It would mean humanity had learned how to manufacture cosmic geography. It would mean distance had become something editable. It would mean the map of the universe was no longer only discovered, but revised. At that point, calling us spacefaring would be inadequate. We would be spacetime engineering. The difference matters. A spacefaring civilization moves through the universe. A spacetime engineering civilization changes the allowed paths. One accepts the terrain. The other cuts tunnels through reality. No evidence says we will reach that stage. No responsible scientist can promise that a wormhole to Andromeda will ever be possible. The safest answer is that known technology cannot do it, and known physics does not give us a practical recipe. But the question remains useful because it exposes the limits of ordinary thinking. When people ask whether humans can reach another galaxy, they often imagine the answer depends on better propulsion. A more powerful engine, a cleaner fuel, a ship that goes faster. Andromeda teaches a harsher lesson. Better propulsion helps until the scale overwhelms the category. Then the problem becomes not merely how to move, but how to survive time, how to preserve identity, how to manage energy on absurd scales, and whether spacetime itself has hidden roots. The galaxy we can see becomes a test of what kind of species we imagine ourselves becoming. Maybe the first emissaries to Andromeda will not be human bodies. Maybe they will be small probes accelerated by laser arrays, crossing intergalactic space for millions of years, silent through the dark, waking only when the galaxy fills their instruments. They may carry no voices, only instructions etched into circuits, descendants of our machines rather than our blood. Maybe they will be self-repairing craft capable of harvesting material from interstellar dust or rogue objects, rewriting their own systems as they move. Maybe they will be artificial minds, if such minds can exist, carrying human questions in non-human forms. Maybe nothing we launch will ever arrive. Maybe Andromeda remains an object of sight, not contact. That possibility should not be treated as failure. There is a strange dignity in knowing the boundary. Science is not only the art of reaching, it is also the art of measuring the walls of the possible and refusing to lie about their height. Andromeda is already connected to us by light. That is not a metaphor. Photons from its stars and nebulae cross the gap and enter our telescopes. We collect them. We sort them by wavelength. We measure their spectra. We infer chemical composition, motion, temperature, dust, star formation, and structure. We have built instruments that turn ancient light into knowledge. In that sense, we have touched Andromeda without traveling there. Astronomy is remote contact. Every telescope is a kind of time machine that only looks backward. We cannot change what we see. We cannot warn the stars. We cannot ask the galaxy what it is doing now, because now is not a simple thing across millions of light years. The Andromeda we observe is Andromeda as it was when its light left. Its current state in the ordinary Earth sense is hidden from us by distance and the speed of causality. This is another reason the idea of reaching it feels so strange. To travel to Andromeda is not only to cross space. It is to try to enter a place we have only known in the past. If a ship left tomorrow and somehow arrived, it would not arrive at the Andromeda we see tonight. It would arrive at Andromeda millions of years later. The galaxy would have rotated. Stars would have died. Others would have formed. Supernova remnants would have expanded. Binary systems would have changed. Civilizations, if any existed there, could rise and vanish while their light was still in transit. The target is alive in time. Our image is delayed. The night sky is not a live broadcast. It is an archive. That archive can be intimate. The photons that reach your eye from Andromeda have traveled longer than human civilization has existed. Yet the final act of their journey happens in your retina. A quantum of light crosses intergalactic space and ends as a signal in a human nervous system. The scale is absurd. The contact is real. Maybe that is why Andromeda feels close, because seeing is a form of arrival for light, not for us. The most honest answer to the episode's central question is layered. Could we reach Andromeda with present technology? No. Could a future civilization send a probe using advanced but still imaginable physics? Perhaps, if it accepts mission durations measured in millions of years or develops relativistic systems beyond our current capabilities. Could humans travel there in a way that feels like a human journey? Only with technologies that are speculative at best. Extreme relativistic ships, suspended animation, generation habitats, artificial minds, or some form of transformation we do not yet understand. Could a wormhole make the journey short? In theory, only if traversable wormholes are physically possible, stable, controllable, and connectable to useful destinations. None of that is known. Could physics forbid every practical version? Yes, that remains possible. The door is not open. It is not closed in the simple way fantasy skeptics sometimes imply. It is cracked in mathematics, sealed in engineering, and silent in observation. That silence is important. No known wormhole waits near Earth. No signal has revealed a shortcut through spacetime. No experiment has shown that negative energy can be gathered at the scale required to hold open a human-sized throat. No mission plan exists that turns Andromeda into a practical destination. But the lack of a route does not make the question empty. Some questions are valuable because they show us where the edges are. Andromeda is an edge disguised as a blur. A child can see it. A civilization may never reach it. That contradiction is the heart of the episode. There is something humbling about a visible impossibility. Usually, what is impossible is hidden from us. We do not see the bottom of the ocean from a mountain road. We do not see the interior of a neutron star when we look at a point of light. But Andromeda places the unreachable in plain sight. It says, here is another galaxy. It says, your eyes can receive it. It says your engines cannot go there. For most of human history that would have been enough. The galaxy was a mist, then a nebula, then an island universe. Our understanding changed, but our bodies remained fixed to Earth. Then rockets came, and the moon became reachable. Probes crossed the solar system. Machines entered orbit around other worlds. Human imagination expanded with every mission. It is tempting to extend that curve forever. First the moon, then Mars, then the outer planets, then the stars, then the galaxies. But the universe is not obligated to make progress feel smooth. The jump from planets to stars is enormous. The jump from stars to galaxies is worse. The space between galaxies is not just more of the same road, it is the place where our assumptions about travel begin to fail. A civilization may fill its solar system and still never become intergalactic. It may build habitats around the sun, mine asteroids, settle moons, send probes to nearby stars, and still regard Andromeda as we regard the edge of a dream. That possibility changes the emotional shape of the future. Science fiction often gives civilization the galaxy. Then it gives civilization many galaxies. The scale becomes a stage for politics, war, trade, and empire. But real physics may keep intelligent life more local, clustering around stars, perhaps moving slowly through the Milky Way, perhaps never crossing the dark between great galaxies except by light and machines that no one waits for. If that is true, the universe may be full of islands that know of one another and never meet, not because they are alone, because distance is a deeper prison than loneliness. This thought touches the Fermi paradox from another angle. We often ask why we do not see alien civilizations. We wonder whether they are rare, silent, extinct, hidden, or uninterested. But even if civilizations are common, and even if some become old, the distances between galaxies may still impose a kind of cosmic separation. Interstellar travel is already hard. Intergalactic travel may be a filter so severe that even advanced life remains bound to its galactic home. Andromeda is nearby enough to remind us that other islands exist. It is far enough to make reaching them almost metaphysical. A wormhole, if one could exist and be controlled, would transform that picture. It would make the universe less like islands and more like a network. It would make separation negotiable. Civilizations with wormholes would not merely expand, they would redefine locality. Two places could be millions of light-years apart through normal space and seconds apart through engineered geometry. But such power would come with risks we can barely name. A wormhole network could carry radiation, gravitational disturbances, invading matter, causal paradoxes, or instabilities. It could connect regions with different histories and dangerous environments. It could turn cosmic distance, which currently protects everything from everything else, into a membrane with doors. Distance is not only an obstacle, it is also a shield. Andromeda cannot harm us quickly, because it is far away. A supernova there is ancient news when we see it. A civilization there, if one existed, could not easily reach into our sky. The speed of light enforces quarantine. The universe is enormous, and that enormity keeps events separated. To break distance is to break one of the universe's safety features. This is why the dream of wormholes should feel unsettling, not merely exciting. A shortcut through spacetime would be the most powerful infrastructure ever imagined. It would make roads out of geometry. It would also make causality, security, and identity into engineering problems. Perhaps that is why nature does not appear to hand out wormholes casually. Or perhaps they exist and are rare, hidden, microscopic, unstable, or impossible to recognize with current instruments. We do not know. The phrase "we do not know" is not a weakness here. It is the most accurate place to stand. Good science does not turn every unknown into a promise. It also does not flatten every speculation into nonsense. It separates what is observed, what is allowed by models, what is conjectured, and what is desired. Andromeda is observed, its distance is measured, relativity is tested. The light speed limit is foundational to modern physics. Traversable wormholes are theoretical. Negative energy at useful scales is not demonstrated. Intergalactic travel remains beyond any known engineering. The wonder survives the honesty. In fact, it becomes stronger. A false promise is cheap. A real boundary is profound. When you look at Andromeda, you are not seeing a future vacation spot. You are seeing a problem large enough to expose the architecture of reality. You are seeing light that crossed a distance we cannot cross. You are seeing the difference between information and presence. Information travels to us. Presence may not. That difference shapes the entire human relationship with the cosmos. We know far more than we can touch. We can measure planets around stars we will never visit. We can infer black holes from radiation and motion. We can map the cosmic microwave background, ancient light from the early universe, while remaining trapped around one ordinary star. Our knowledge outruns our bodies. Andromeda makes that visible. The galaxy is not only an object, it is a mirror held up to human ambition. In that mirror, we see our machines, our theories, our myths of progress, and our impatience with distance. We also see something quieter. We see that understanding does not always require possession. We may never stand under an Andromedan sky. We may never watch the Milky Way rise from one of its worlds. We may never send a human voice across that gulf and hear an answer. Yet we can know it is there. We can map its stars. We can study its motion. We can ask what it would take to reach it, and by asking, discover the shape of the laws that hold us here. There is a kind of intimacy in that. Not the intimacy of touch, the intimacy of attention. Imagine, far in the future, a machine leaving the outskirts of the solar system. Behind it, the sun is already only one star among many. The planets are memories in its navigation logs. Ahead, the Milky Way thins, not suddenly, but gradually, until the familiar density of stars gives way to a darker sea. The probe carries maps, instruments, perhaps a message, perhaps only code. It does not sleep because it is not alive in the way we are alive. It waits, it corrects its course, it survives radiation and dust, it watches the Milky Way shrink behind it and Andromeda grow ahead of it with unbearable slowness. No human controller remains from the launch generation. No original language remains unchanged. Perhaps Earth is alive. Perhaps Earth is not. Perhaps the descendants of humanity have become many things. Perhaps no one remembers the probe except in archives. Still it moves. This may be the most realistic form of intergalactic ambition. Not conquest, not migration. A durable question sent into the dark. But if a wormhole were possible, the image changes completely. Imagine a ring or sphere of engineered spacetime floating beyond the orbit of Neptune, surrounded by power systems larger than planets, guarded by machines that watch the stability of the throat. On one side, our solar system. On the other, not a view through a window exactly, but a connected region of spacetime whose other mouth opens somewhere near Andromeda. A ship enters slowly. Locally, it never breaks the speed of light. It crosses a short path. It emerges into another galaxy. The journey that should have taken millions of years becomes an event. If such a thing were real, the first crossing would be one of the most dangerous acts in history, not because of aliens or monsters, but because the civilization crossing would be testing whether its understanding of reality was strong enough to survive contact with its own technology. The ship would not just go to Andromeda. It would prove that distance had become conditional. That proof would change everything. Trade, exploration, warfare, communication, astronomy, even the meaning of home would shift. A colony across the universe could be nearer than a moon if connected by geometry. A disaster could travel through a shortcut. A message could outrun light by using a route that makes the normal route irrelevant. Causality questions would stop being abstract. The universe would become smaller in practice while remaining enormous in fact. That is the paradox of a wormhole civilization. It does not shrink the cosmos. It edits the paths through it. The problem is that every piece of this picture rests on unknowns stacked on unknowns. We do not know whether macroscopic traversable wormholes can exist. We do not know whether exotic matter can be produced. We do not know whether quantum effects destroy the stability of would-be time machines. We do not know how a civilization could create, aim, anchor, or protect such a structure. We barely know how to leave our own planet sustainably. That contrast matters. There is a danger in speaking about wormholes too casually. It can make the future feel guaranteed, as if every unsolved problem is only a delayed invention. But the universe is not a technology tree. Some doors may be locked by law, not by difficulty. Some things may be imaginable because mathematics is generous, while reality is not. The history of science contains both kinds of surprise. Flight looked impossible until it was not. Nuclear energy looked impossible until physics opened the nucleus. Space travel looked impossible until rockets became powerful enough. But perpetual motion remained impossible, not because engineers lacked dedication, but because thermodynamics does not negotiate. Where do wormholes belong? We do not know. They may be like flight, waiting for deeper understanding. They may be like perpetual motion, a beautiful misunderstanding of what equations permit under idealized conditions. They may exist only as quantum features too small and unstable for travel. They may be forbidden by a principle we have not fully grasped, or they may be possible only for civilizations whose energy scales and scientific maturity are so far beyond ours that describing them as descendants of us becomes more poetry than prediction. Andromeda forces this humility, because without something as radical as a wormhole, the path remains almost unbearable. Even a near-light-speed mission carries questions that do not feel like engineering details. How does a ship protect itself from dust for millions of Earth years? How does it maintain aim? How does it power itself? How does it communicate across intergalactic distance? How does anyone back home wait for a reply? A signal from Andromeda takes 2.5 million years to return after arrival. A round-trip conversation, even by light, is 5 million years. This means a mission to Andromeda cannot be managed in the ordinary sense. There is no real-time control, no rescue, no adjustment from mission headquarters. The probe or crew must become autonomous at a level that makes it less like an expedition and more like an independent branch of history. The sending civilization gives up control at launch. This is true even for nearby stars, but Andromeda amplifies it until it becomes existential. The distance does not merely delay communication. It ends the possibility of shared present tense. Earth and the traveler no longer live inside one practical now. They are connected by causality, but not by conversation. A wormhole would alter that too. If stable and usable, it could allow travel and perhaps communication over the shortcut. But then the wormhole itself becomes the fragile artery. Destroy it and the distant colony becomes lost behind millions of years of ordinary light travel. Control the wormhole, and you control access to another galaxy. Again, infrastructure. Again, power. Again, danger. The first off-world civilizations may build habitats, stations, and planetary bases. But a wormhole civilization would build geography. It would decide which places are near. It would make maps political, in a way deeper than borders. A point in Andromeda connected by wormhole could be economically closer than a planet in the outer solar system without one. The old meaning of distance would fracture. This is the hidden theme inside the Andromeda question. Reachability is not fixed. It depends on the allowed paths. For humans walking, a mountain is a wall. For aircraft, it is terrain. For radio, it is partly transparent. For light, vacuum is a road. For massive bodies, light speed is a limit. For a wormhole, if one can exist, geometry itself becomes the road. Every technology changes the map. Andromeda asks whether there is a technology that can change the map enough. Maybe there is not. Maybe the final answer is that galaxies are visible but effectively sealed from one another, except through slow light and slower matter. Maybe intelligence blooms in separate galactic gardens, each seeing the others as faint islands in the dark, each making myths of impossible travel, each learning that knowledge can cross where bodies cannot. That would be a lonely universe. It would also be a beautiful one, because even sealed islands can see. Light is the universe's ancient messenger. It carries no passports. It asks no permission. It leaves a star, crosses emptiness, and arrives wherever geometry allows. The photons from Andromeda have been falling into Earth's night for longer than our species has had Zions. They fell on forests, ice ages, oceans, deserts, cities, battlefields, observatories, and quiet hillsides where someone looked up and saw only a blur. Every generation that saw it saw the same galaxy and a different meaning. To some, it was a cloud. To others, a nebula. To modern astronomy, another spiral system in the local group. To us tonight, it is a question: can we ever reach it? The deepest answer may be that we do not yet know what reaching will mean. A medieval sailor and a radio engineer do not mean the same thing by contact. A hunter walking across a valley and a spacecraft receiving a signal from Mars do not mean the same thing by arrival. A future mind copied into a probe, a generation ship culture, a wormhole traveler, and a telescope observer may each claim a different kind of reach. Perhaps humanity reaches Andromeda first by understanding it, then by sending machines, then by sending descendants, or perhaps never. Perhaps the galaxy remains forever on the other side of a boundary that no engine crosses and no wormhole opens. There is no shame in that possibility. The universe is allowed to be larger than our ambitions. It is allowed to contain visible things that remain untouched. The desire to go is human. The refusal of the distance is cosmic. And yet, the question will not leave us alone. That is also human. We are the species that sees a faint blur and asks how to get there. We are the species that turns a smudge into a distance into an equation into a machine, and a machine into a story about who we might become. Andromeda is not empty space on the far side of the night. It is a test. It tests our engines. It tests our patience. It tests our theories of time. It tests our definitions of self. It tests whether the word possible is a description of current tools or a permanent feature of reality. For now, the galaxy remains where it has always been from our perspective, above us, beside us in the local group, approaching or perhaps not quite destined in the way we once thought, visible and unreachable, intimate and impossible. The sky offers it without explanation. A faint blur, a neighboring galaxy, a 2.5 million year crossing of light, a place we may never enter unless we learn to move not only through space, but through the hidden geometry beneath it. And maybe that is the real lesson. The universe does not only separate things by distance, it separates them by what kinds of motion are allowed. To reach Andromeda, we may need more than courage, more than engines, more than time. We may need a new command of reality itself. Until then, the nearest great galaxy remains a paradox in the dark, close enough for the eye, too far for the hand. There is another way to feel the scale, and it begins with patience rather than speed. Imagine placing a clock beside every ambition humans have ever had. One clock for a human life, one for a civilization, one for a species, one for a mountain range, one for a galaxy. Most of our plans are built for the first two clocks. We save money, build cities, write laws, launch missions, and imagine futures that fit inside decades or centuries. Even our longest political dreams are short compared with the life of a star. Andromeda belongs to another clock. The distance to it is so large that even light, the fastest signal the universe permits, turns into a historian. It does not carry news. It carries fossils of light. When we look at Andromeda, we are not sharing a moment with it. We are receiving a message from a galaxy as it was when early humans were not yet building the world that would eventually build telescopes. That matters for travel because a journey is not just a line on a map. It is a line through time. The ship that crosses to Andromeda has to survive the external universe and its own internal future. Metal fatigues, electronics decay, radiation damages materials, stored fuel changes. Computers become obsolete only in our culture, but in space, they also become physically vulnerable. A mission lasting millions of years must either preserve itself with impossible reliability or become capable of endless renewal. Self-repair is not a convenience at that scale. It is the mission. A ship to Andromeda would need to mine, recycle, rebuild, and diagnose itself without help. It would need to carry factories, not just spare parts. It would need to understand its own design well enough to replace pieces whose makers died ages earlier. It would need to adapt to unknown damage without a human engineer on Earth answering a call. This points toward a future where the boundary between spacecraft and organism becomes blurred. Living things survive by repair, replication, adaptation, and selection. A truly long-duration probe may need some version of those principles, whether biological, mechanical, or computational. It may need to become less like a bullet and more like a seed. A seed is a strange comparison for an intergalactic machine, but it fits. The seed carries compressed instructions through an interval of danger. It waits for conditions. It unfolds only when the environment allows. An Andromeda probe might spend most of its life inert, conserving energy, protecting memory, correcting course with tiny adjustments, and waking fully only when the target galaxy becomes a place rather than a light. The dream of reaching Andromeda may therefore belong less to astronauts and more to seeds, not flags planted under alien stars, but patient machines carrying small fragments of Earth's curiosity across a distance that no living witness can hold in memory. This is not as romantic as a crew stepping onto a world beneath an Andromedan sky. It is colder. It is quieter. It may also be closer to reality. Yet even a seed probe raises the problem of purpose. Why send it? Science, perhaps. Legacy, perhaps. A need to know whether a thing can be done. But the return of knowledge is blocked by the same distance. A probe arriving in Andromeda and transmitting home would send a signal that takes another 2.5 million years to return. By then, the listeners would not be the senders. They might not exist at all. So the mission cannot be justified only by feedback. It must be justified by offering a gift to a future so remote that it becomes almost abstract. The senders act without knowing who, if anyone, receives the result. That is an ethical and emotional structure closer to building cathedrals than launching satellites. People built stones into ceilings they would never see completed. A civilization might launch a probe whose message it will never hear returned. Andromeda turns exploration into faith without asking us to abandon science. It asks whether knowledge is worth creating when the knower may be gone. The answer may be yes. A civilization mature enough to attempt intergalactic missions might not think only in lifetimes. It might think in continuities, archives, and descendants. It might create institutions designed not for elections or markets or even centuries, but for million-year memory. Such institutions do not exist now. We barely preserve data across decades without format decay, institutional collapse, or neglect. Yet a journey to Andromeda would require memory as engineering. The greatest challenge may not be propulsion. It may be continuity. The ship must remember where it is going. The culture must remember why it was sent. The machines must remember how to repair themselves. The descendants, if any, must remember what arrival means. Without memory, motion becomes drift. This is why wormholes feel so seductive. They rescue us from continuity. They promise that the journey can become short enough for ordinary meanings to survive. Departure and arrival can belong to the same generation. A message can be answered. A traveler can return. A civilization can maintain a relationship with a distant place without wading through geological time, but shortcuts often transfer difficulty rather than remove it. A wormhole replaces the problem of patience with the problem of power. It replaces slow survival with extreme control. It replaces the ship's long vulnerability with the throat's stability. It asks for exotic energy, causal discipline, and mastery of spacetime geometry. It may be the more elegant dream, but not the easier one. There is something almost moral in that trade. The universe allows no cheap road to another galaxy. It demands either endurance beyond imagination or physics beyond possession. That is why Andromeda is such a clean dark matter radio question. It does not need monsters. It does not need hidden aliens. The terror is already in the numbers. The mystery is already in the geometry. The emotional weight is already in the fact that anyone with dark skies can look at the destination. A person can stand on Earth, cold air on their face, and see the whole problem at once. A faint blur, a visible galaxy, a journey almost no version of us can make. The view is simple, the implication is not. There is another way to feel the scale, and it begins with patience rather than speed. Imagine placing a clock beside every ambition humans have ever had. One clock for a human life, one for a civilization, one for a species, one for a mountain range, one for a galaxy. Most of our plans are built for the first two clocks. We save money, build cities, write laws, launch missions, and imagine futures that fit inside decades or centuries. Even our longest political dreams are short compared with the life of a star. Andromeda belongs to another clock. The distance to it is so large that even light, the fastest signal the universe permits, turns into a historian. It does not carry news. It carries fossils of light. When we look at Andromeda, we are not sharing a moment with it. We are receiving a message from a galaxy as it was when early humans were not yet building the world that would eventually build telescopes. That matters for travel because a journey is not just a line on a map. It is a line through time. The ship that crosses to Andromeda has to survive the external universe and its own internal future. Metal fatigues, electronics decay, radiation damages materials, stored fuel changes, computers become obsolete only in our culture, but in space they also become physically vulnerable. A mission lasting millions of years must either preserve itself with impossible reliability or become capable of endless renewal. Self-repair is not a convenience at that scale. It is the mission. A ship to Andromeda would need to mine, recycle, rebuild, and diagnose itself without help. It would need to carry factories, not just spare parts. It would need to understand its own design well enough to replace pieces whose makers died ages earlier. It would need to adapt to unknown damage without a human engineer on Earth answering a call. This points toward a future where the boundary between spacecraft and organism becomes blurred. Living things survive by repair, replication, adaptation, and selection. A truly long-duration probe may need some version of those principles, whether biological, mechanical, or computational. It may need to become less like a bullet and more like a seed. A seed is a strange comparison for an intergalactic machine, but it fits. A seed carries compressed instructions through an interval of danger. It waits for conditions. It unfolds only when the environment allows. An Andromeda probe might spend most of its life inert, conserving energy, protecting memory, correcting course with tiny adjustments, and waking fully only when the target galaxy becomes a place rather than a light. The dream of reaching Andromeda may therefore belong less to astronauts and more to seeds, not flags planted under alien stars, but patient machines carrying small fragments of Earth's curiosity across a distance that no living witness can hold in memory. This is not as romantic as a crew stepping onto a world beneath an Andromedan sky. It is colder. It is quieter. It may also be closer to reality. Yet even a seed probe raises the problem of purpose. Why send it? Science, perhaps. Legacy, perhaps. A need to know whether a thing can be done. But the return of knowledge is blocked by the same distance. A probe arriving in Andromeda and transmitting home would send a signal that takes another 2.5 million years to return. By then, the listeners would not be the senders. They might not exist at all. So the mission cannot be justified only by feedback. It must be justified by offering a gift to a future so remote that it becomes almost abstract. The senders act without knowing who, if anyone, receives the result. That is an ethical and emotional structure closer to building cathedrals than launching satellites. People built stones into ceilings they would never see completed. A civilization might launch a probe whose message it will never hear returned. Andromeda turns exploration into faith without asking us to abandon science. It asks whether knowledge is worth creating when the knower may be gone. The answer may be yes. A civilization mature enough to attempt intergalactic missions might not think only in lifetimes. It might think in continuities, archives, and descendants. It might create institutions designed not for elections or markets or even centuries, but for million-year memory. Such institutions do not exist now. We barely preserve data across decades without format decay, institutional collapse, or neglect. Yet a journey to Andromeda would require memory as engineering. The greatest challenge may not be propulsion. It may be continuity. The ship must remember where it is going. The culture must remember why it was sent. The machines must remember how to repair themselves. The descendants, if any, must remember what arrival means. Without memory, motion becomes drift. This is why wormholes feel so seductive. They rescue us from continuity. They promise that the journey can become short enough for ordinary meanings to survive. Departure and arrival can belong to the same generation. A message can be answered. A traveler can return. A civilization can maintain a relationship with a distant place without wading through geological time. But shortcuts often transfer difficulty rather than remove it. A wormhole replaces the problem of patience with the problem of power. It replaces slow survival with extreme control. It replaces the ship's long vulnerability with the throat's stability. It asks for exotic energy, causal discipline, and mastery of spacetime geometry. It may be the more elegant dream, but not the easier one. There is something almost moral in that trade. The universe allows no cheap road to another galaxy. It demands either endurance beyond imagination or physics beyond possession. That is why Andromeda is such a clean dark matter radio question. It does not need monsters. It does not need hidden aliens. The terror is already in the numbers. The mystery is already in the geometry. The emotional weight is already in the fact that anyone with dark skies can look at the destination. A person can stand on Earth, cold air on their face, and see the whole problem at once. A faint blur, a visible galaxy, a journey almost no version of us can make. The view is simple. The implication is not. Subscribe to Dark Matter Radio if you want more long journeys through the parts of science that do not become smaller when we understand them. Leave a comment with the question Andromeda leaves in your mind. Would you still call it human exploration if only our machines, our descendants, or our altered minds could ever arrive? And as always, keep listening to the dark.